All right, so welcome to the 791st monthly meeting of EPAASM. Happy New Year. This is our first of 2022. Today we have Dr. Rebecca Dunn, who will tell us about the 16S RNA gene PCR using in the clinic. As always, ASM appreciate your support. Joining the membership will advance your science, your career, nurture this network and the community. And I think we're still in the process of using this ASM Connect, where you can join a conversation with your peers in different parts of the country, in the world, and you can participate in discussion. They're also member-only events. And to go along with that, our branch, this is our 101st year of the branch, and we are one of the oldest branch as well as one of the most active branch. And as you can see, we have monthly meetings where we bring in the lectures. We have our annual clinical microbiology symposium. The last November one was our 50th symposium. And we also have our annual Philadelphia Infection and Immunity Forum. And the last one was our 30th. And as well as we have a lot of scientific outreach and education programs. And all these are possible because of members, your support, our very active and dedicated student chapter, as well as our education committee and our executive committee. So please join the branch or renew your membership so we can keep bringing you science and nurture this unique community. Just a reminder, we'll keep all the questions to the end. You can either use the participant button and raise a little blue hand. Jason and Kyle will moderate the Q&A at the end, and they can unmute you so you can ask your questions in person or via video, or you can type in the chat box and then they can relay the questions. And now Kyle Rodino is going to introduce Dr. Dunn.
Thanks, and welcome everybody again. It really is my pleasure to introduce today's speaker, Dr. Rebecca Dunn. Dr. Dunn is currently the Senior CPEP Fellow in Medical and Public Health Microbiology, which is a combined fellowship with the Hospital of the University of Pennsylvania and Children's Hospital of Philadelphia. Rebecca found her way to Penn via the University of Delaware, where she received her Bachelor's of Science with distinction in biochemistry, and then Duke University, where she received her PhD in molecular genetics and microbiology studying influenza viruses under the tutelage of Dr. Nicholas Heaton. During her time at Duke, Dr. Dunn gained exposure to clinical microbiology in their clinical microbiology laboratory, leading her to pursue additional training here at Penn. Rebecca has been an exceptionally productive fellow, working on a number of new assay validations here and at CHOP, including optimization of SARS-CoV-2 testing. She's participated in a study of antimicrobial resistance of gram-negative bacteria from isolates collected in Botswana. And she's looking at the clinical utility and the need for diagnostic stewardship with advanced molecular diagnostics. Specifically, those projects include the use of the Carius plasma cell-free metagenomics assay at CHOP and broad-range bacterial PCR sequencing here at HUP, the latter of which she will discuss with us this evening in her talk titled Clinical Utility of Broad-Range 16S rRNA Gene PCR with Sequencing. It truly has been a pleasure to have Rebecca as our fellow, and I'm very excited to see all that she'll accomplish in her career and have her as a colleague for many years to come. So without further ado, I will turn it over to Dr. Dunn.
Thank you so much, Kyle, for that very kind introduction and for the invitation to share some of my work today. So in my fellowship, as Kyle mentioned, I train at both the Hospital of the University of Pennsylvania and the Children's Hospital of Philadelphia. So today I decided to share a project incorporating some data from both of these institutions. This project is reviewing the clinical utility of broad-range 16S PCR with sequencing. And today I'll discuss both a retrospective review of the use of this assay at these institutions, as well as talking about some practical stewardship guidelines. So first, I want to start off with some context for the spectrum of diagnostics that are available to detect a pathogen in a clinical specimen. On the far side of the spectrum, with conventional microbiologic testing, it includes assays like stains and smears, culture, and antigen testing. Next, molecular testing was introduced first with targeted PCRs, which detects only a single pathogen of interest. And these assays have become routine in the clinical lab as they are sensitive, specific, as well as faster than many culture methods. Multiplex PCRs build on that same concept, although they use multiple targets to detect a panel of pathogens that commonly cause a clinical syndrome. So these are often known as syndromic panels. And then lastly, my focus is within the category of advanced molecular diagnostics. In this category, broad-range PCR is a sequencing-based method of identification, which can detect a pathogen within a given class of organisms. So depending on the design of the assay, it can target bacteria, mycobacteria, fungi, parasites. And then the most novel advanced molecular technology that is currently available in clinical microbiology is shotgun metagenomics. And this is an entirely unbased sequencing strategy to identify pathogens in a clinical sample. So for this talk, I'm going to focus on broad-range PCR and sequencing. Broad-range PCR is a well-established technology. It has been around for well over 30 years. It was originally used for phylogenetic characterization, as by sequencing a conserved gene across a given class of organisms, you can map similarities and differences to create phylogenetic trees. But it originally began being used clinically starting around 2000. So what is broad-range PCR? It is very simplest. It is a targeted PCR which generates an amplicon that can be sequenced and used to identify the organism. The idea is that it has the broad ability to target organisms within a given class. So again, depending on the assay, you can target bacteria, fungi, or parasites, just depending on the gene. But for the purpose of this talk, I will be focusing on bacterial broad-range PCR, which is the most widely used target for most clinical applications. And while I'll be referring to it for the most part as broad-range PCR for this talk, within the diagnostic microbiology community, it is interchangeable with terms like universal PCR, 16S rRNA sequencing, or ribosomal sequencing, if these are more familiar to you. In the clinical lab, there are several potential applications of broad-range PCR. Prior to routine use, it was used to discover several unknown pathogens and link them to the corresponding clinical syndrome, and I've listed a few of the most famous examples of this here. Another application, and one that is common in many large clinical labs, is the use of isolate identification from pure culture. So this is for cases where other routine methods of identification, such as MALDI-TOF or biochemicals, have failed to provide an identification. You can escalate to this molecular method. And then lastly, bacterial broad-range PCR can be used for pathogen identification directly from clinical specimens. And so this is limited to sterile specimens only, and is especially relevant if the organism wasn't detected by culture. So this can commonly happen for two reasons. Either the organism is fastidious, such that it doesn't grow in traditional culture media, or if antibiotics were administered to the patient prior to collection of the specimen, you similarly might see negative cultures despite there being a causative organism. So for this talk, I'm going to focus on this last application, the identification of pathogens directly from clinical specimens. And again, while this is not novel technology, this last application is unique in the sense that it has limited availability. So most assays that are able to detect pathogens directly from clinical specimens are available only at reference laboratories. And a lot of that is due to the fact that the workflow for this assay is highly manual and technically complex. So the workflow for bacterial broad-range PCR breaks down into three steps. The first is extraction of the bacterial DNA and amplification of the 16S rRNA gene. So the entire 16S gene is about 1,500 base pairs long, although that varies across species, and it codes for part of the 30S small subunit of prokaryotic ribosomes. Most clinical assays are designed to target about a 500 base pair portion of this gene, most commonly the V1 to V3 variable regions, although assays can vary. And for increased specificity, you can target the entire 1.5 kb region. So critically, for the design of the assay, the primers will target conserved regions of this gene that are present in all bacteria, but then amplify adjacent variable regions, which differ enough between species that they can identify the bacteria to the genus and species level. The next step in this process, the generated amplicon is sequenced. This can be done either through using Sanger methodology, which is fast and cheap, but unable to resolve multiple targets, or using next generation sequencing, which is more expensive, but can differentiate multiple bacteria present in a sample. And these platforms also have differences in their throughput and speed as well. Finally, the last step in this workflow is the comparison of the sequence reads to a database for identification. So at this point, sequence quality, of course, is important, but similarly, the breadth and quality of the database that you're comparing your sequence to plays an important role. So there are both publicly and commercially available reference databases. They have varying degrees of curation, and several of which I've listed here. So this curation ensures the quality of the uploaded sequence data, and also helps keep up with any taxonomy changes of clinically relevant bacteria. Overall, this is a fairly work-intensive process. It requires a lot of quality checks and controls to ensure the accuracy of the generated identification. And I thought I would just kind of open up with a case study from the Hospital of the University of Pennsylvania to demonstrate some of the power of this assay when other diagnostic options have failed to identify an etiology. So this was a case of a 60-year-old male with a significant history of hyperlipidemia and chronic sinusitis. He originally presented with left lower extremity numbness and weakness. His workup revealed transient ischemic attack and left lower extremity embolus, as well as a transesophageal echo that was consistent with a mitral valve vegetation. So despite the suspicion for infectious endocarditis in this case, several sets of blood cultures, which are the mainstay for the diagnosis of infective endocarditis, remained negative. And similarly, the serologic workup for pathogens was unrevealing. So next, an embolectomy was performed. This similarly had negative cultures. And finally, a mitral valve repair with a pericardial patch of the mitral valve leaflet was performed, and still no organisms grew in culture from this specimen. However, when a small piece of the valve was sent for broad-range PCR and sequencing, it identified Cardiobacterium hominis, and the team was able to appropriately target therapy for this patient. So as this case highlights, infective endocarditis is one of the clinical indications for which broad range has showed pretty incredible benefit, but it's not the only one. It has also added significant diagnostic value as a tool for the diagnosis of infective endocarditis, bacterial meningitis, and bone infections. So just to go through each of these briefly, infective endocarditis is a subacute process where several features play into the challenges of conventional culture methods to detect the causative pathogen. The first of these is the potential administration of antibiotics prior to surgery to obtain the optimal valve specimen that would be used for culture. There also will be limited specimen available from that type of sampling. So from a prosthetic valve especially, sampling error can be an important source of diagnostic error just because of the limited specimen availability. And then lastly, infective endocarditis can be caused by atypical organisms that may not readily grow in culture. So just to highlight the comparison between culture and broad-range PCR, This study prospectively enrolled 68 patients who underwent heart valve replacement for suspected or confirmed infective endocarditis. And they evaluated the performance of the molecular test, broad-range PCR, against gram stain and culture of the valve tissue. They found the sensitivity of broad-range to be about 2 times higher than that of valve tissue culture, although specificity was slightly lower. And these results have been replicated in cohort studies since then. For bacterial meningitis, again, antibiotics are often rapidly administered and can occasionally preclude the collection of an appropriate specimen. So again, this makes a molecular approach appealing as it can help to narrow antibiotics by providing an identification despite negative cultures. And this, I will say, is especially true for healthcare-associated ventriculitis and meningitis, as these can be caused by a different spectrum of microorganisms than those that are in targeted molecular assays or syndromic panels. So here, the breadth of broad-range PCR adds additional benefit even beyond the targeted assays. So in this study, the authors compared culture to broad-range PCR for the diagnosis of bacterial meningitis. They found that the sensitivity was 90% compared to 78% in culture, and specificity was excellent for both modalities. Lastly, bone and joint infections are often caused by slow-growing, difficult-to-culture organisms, which are easier to detect using molecular methods. So in this study, 525 bone and joint samples were cultured and submitted to broad-range PCR as well as culture methods. Overall, they found the sensitivity was 87 and 93%, and specificity was 89 and 96%, and that's for culture and broad-range PCR, respectively. So while broad-range adds clear diagnostic value for these indications, there have been several recent reviews published by reference labs that review its overall use and reports an overall low positivity rate. So the first of these, the overall positivity rate was 17.1%, 97 positive specimens out of a total of 566 tested. And the second showed a positivity rate of 13.6%, with just 100 out of 734 total specimens set for broad range. So for this reason, a generally low positivity rate, many laboratories have this test under diagnostic stewardship. So just briefly, I'll go through. Diagnostic stewardship can be broadly defined as the use of the right test in the right patient at the right time. And there are many reasons why advanced molecular diagnostics lend themselves to a laboratory stewardship process. The first being that there are technical caveats of these technologies that are not as familiar to providers compared to the decades of experience that clinicians have with routine culture-based or even the more straightforward molecular technologies. There can often be misconceptions about the sensitivity and specificity for these advanced molecular diagnostics. And these make the clinical interpretation challenging. The two biggest clinical concerns for these assays are the possibility of false positive results leading to further invasive diagnostic testing or even unnecessary treatment, or generally the inappropriate interpretation of test results leading to diagnostic errors. Lastly, from a laboratory management perspective, these tests are far more expensive than conventional culture methods. So this consideration is less applicable when we're talking about an individual patient, since it could be well worth the investment in the context of the cost of care for a medically complex patient. But it is, from a laboratory management perspective, important to consider the return on investment compared to alternative available diagnostics. So in starting out this project, I was interested in how we use and steward this assay, as well as how the results of the test ultimately affected patient management. So lastly, I wanted to take a sort of practical approach to formalizing our stewardship process, really evaluate if there were any features of the specimens that we were sending for testing that were associated with either positive test results or beneficial changes to patient management, and then use those features of the specimens themselves to help inform our approval process in terms of which sample should be sent. So for my first goal, I looked at how this test is being utilized. And I performed this review both at HUP and CHOP to evaluate how a single test performed in very different patient populations. So a little bit of background about each of these hospitals. Penn serves predominantly an adult patient population. The capacity at HUP is about 800 beds. They recently added just under 400. The clinical microbiology lab at Penn performs over 300,000 tests per year with just under 40 FTEs, and it is a full-service microbiology lab with bacteriology, mycology, mycobacteriology, parasitology, and molecular sections. At CHOP, it serves predominantly a pediatric patient population with a bed capacity just under 600, though they're soon to add an additional 50. And the infectious disease diagnostic lab at CHOP pre-COVID performed about 150 tests per year, but since taking on COVID testing have increased to over 300,000. They have 45 full-time employees and are, again, a full-service microbiology lab with the exception of currently sending out mycobacteriology due to COVID testing volumes. So while my goal was originally to compare and contrast the broad range test utilization between these institutions, it became pretty clear that these would not be easily comparable for a few reasons. Aside from their different patient populations, I also found that they use different reference labs for their testing. So HUP uses primarily Mayo Clinic, and CHOP sends their specimens to the University of Washington. So these are different assays with theoretically different performance characteristics. Lastly, and probably most importantly for the purposes of a stewardship-based study, HUP has an active stewardship process in place for this assay, while CHOP has no approval process for sending the testing. So just to get a little bit more specific, at HUP, orders are reviewed by laboratory leadership prior to sending this test out to the reference laboratory. So after an order is placed by the clinical team, we reach out to discuss if the source and the available specimen are appropriate for testing and whether or not we should wait for things like routine cultures or maybe even surgical pathology to help inform the choice in specimen that we ultimately want to send. And then once we send the specimen, we find the average turnaround time is about a week. So while there are no strict criteria for this approval process, it is a director level active stewardship process. So to start my review of the utilization of this assay, I pulled the send out data for each of these assays from 2015 through 2020. At HUP, the test was ordered 89 times on 79 individual patients. 3 of these were excluded from my study due to technical inhibition when performing the assay. 2 gave positive but polymicrobial results, and 28 gave positive monomicrobial results. In contrast, at CHOP, the test was ordered 32 times on 28 patients. 1 of these was excluded for technical inhibition, 2 gave polymicrobial results, and 5 gave positive but monomicrobial results. In both of these data sets, I excluded the tests that were never resulted and looked at the remaining orders, so 86 at Penn and 31 at CHOP, and I next separated them by the specimen type that was sent. So at HUP, the breakdown was pretty consistent with what has been published as high-yield sources. So almost 40% of the specimens sent from HUP were heart specimens, with another 10% for prosthetic joint infections, CNS specimens, native joint, and then bone specimens. When we looked at the breakdown of CHOP specimens, we found the breakdown was more heterogeneous. there was only a single heart specimen, but CNS specimens composed about 40% of the orders placed. The rest spanned sterile body sites such as pleural fluid, lymph node, lung, and liver. And if we take a step back, it makes a lot of sense that heart specimens and prosthetic joints would feature more prominently in the adult population, as these are less common concerns in pediatrics. But this brings me to one of my first points, in that this test is extremely flexible in the specimens that are acceptable. So essentially, any sterile body site can be submitted. But unsurprisingly, the patient population that you are testing is going to significantly affect the utilization of the assay. So next, I looked at how the test positivity rate broke down across these different specimen types. At HUP, we had an overall positivity rate of 35%, so 30 out of the 86 specimens were positive. And that broke down across specimens as follows. The CNS had the highest positivity rate, around 56%. Heart and prosthetic joints hovered around 35%, and native joint and bone were lower, just under 15%. At CHOP, 7 out of 31 specimens were positive, with an overall positivity rate of 23%. And then in terms of how this broke down for specimen types, both CNS and pleural fluid had the highest positivity rate, around 35%. So next, I wanted to ask how the test results ultimately influence clinical management. And since the HUP data set was larger, we already have frequent conversations about test utilization. I decided to use that data set to evaluate clinical management and then use this as an opportunity to improve and formalize our stewardship process. And I will kind of come back to a discussion of the CHOP data at the end of the talk. So in reviewing HUP's experience with the test and how it affected clinical management, I defined clinical utility in 3 related ways. The first is the clinical follow-up of results. Second, how the team determined the results, whether or not they determined them to be significant, and then whether or not there was a change in management based on the test results. So we specifically wanted to look at the team's response to the results because this is a send-out test and it has a longer than average turnaround time compared to other microbiology testing. When we characterized the degree of clinical follow-up, we found, unsurprisingly, that over 80% of test results were discussed in a note. Most of the results, when they were not discussed, were negative, and we found a few reasons to explain that. Most patients had a shift in the team managing their care, and therefore no follow-up from the original team, say, for example, infectious disease, who had originally ordered the test. There were also 3 incidences that we found where, in looking back retrospectively, likely these should not have been sent to begin with, as the concern for infection was not particularly high. For samples that were not discussed in the note that had positive results, which is perhaps a more important category, several of these weren't acknowledged since a non-infectious etiology had been identified, or the organism itself had grown from culture before the broad range results were back. We found only a single instance where there was no charted discussion of the broad range results, but continued discussion of possible infectious etiologies. So to dig a little deeper into whether these results were considered clinically significant, we looked at the clinical team's interpretation of either positive or negative, and whether they confirmed or disproved an infectious diagnosis. So here, of the positive results, 26 of them were considered to be the causative pathogen at the time of the resulting, and only 4 were considered clinically insignificant. Of those 4, 2 were considered contamination with normal microbiota. 1, Staphylococcus epidermidis, was discounted as there was a non-infectious etiology identified. And then 1, Streptococcus gordoni, was thought to be more consistent with previous infection than the active disease process. So what we can take away from this is that broad range is generally pretty specific, when positive, and that generally when there was a single pathogen identified, it was believed to be the pathogen of interest. On the other hand, of the orders with negative broad range results, 37 of these were still considered likely infectious, and their antimicrobial therapy was continued. Another 8 were considered potentially infectious, but antimicrobial therapy was continued out of an abundance of caution. And lastly, 10 were discussed as unlikely to have an infectious etiology, and therefore antimicrobial therapy was discontinued. And I'll also point out here that this is an overall small percentage of the total negative results that actually led to a discontinuation in therapy. And I will come back to this idea when talking about clinical utility. So next I want to pivot to our final goal of the study, and that is defining specimen criteria to inform cases where broad-range PCR is most likely to give useful clinical data. And this helps us certainly with our test stewardship efforts. So for this, we set out to see if we could predict positivity of broad-range PCR based on a prior diagnostic workup. So many of these patients had already had extensive infectious workup. They'd had prior blood cultures, cell counts and chemistries, cultures, and surgical pathology. So we focused on the 2 of these that are most common and most appropriate for detecting a bacterial pathogen. These are routine cultures and surgical pathology. Of our 86 orders, we found that 80 of them, or just about 93%, had the appropriate cultures ordered on the specimen that was ultimately sent for broad-range sequencing. But only 47 of them, just over half, had had surgical pathology ordered as well. Next, we used these metrics to develop a scoring system to quantify whether or not the cultures or pathology had clear signs of infection that might help predict broad-range positivity. So we did this with a combinatorial scoring system based on visualized inflammation or organism seen on pathology or on the gram stain from culture. And I'm going to abbreviate this, the VIO score, moving forward for visualized inflammation and organism. So in this system, a sample with a score of 0 would have no inflammation or organism seen on either pathology or gram stain, while a sample with a score of 4 would have evidence of both inflammation and organisms using both testing modality. Out of the 86 samples total, 5 had neither pathology or culture, so we were left with 81 specimens for this predictive analysis. Of these, 29 had a VIO score of 0, 30 with a VIO score of 1, 14 with a VIO score of 2, and then 4 each with a VIO score of 3 and 4. And so this is an intuitive system, but what I hope you can appreciate from this bar graph where you have VIO score on the x-axis and percent positivity of broad range shown in blue is that the positivity rate of our broad range directly correlates with the VIO scoring system of the specimen. In specimens with a low VIO score, we generally found the broad range positivity was limited. So of the 59 specimens with a VIO score of 0 or 1, only 12 had positive broad range results. Of these, several were considered contaminants, leaving only 9 as the causative pathogen. And then breaking down those cases where a pathogen was identified, 4 out of 9 were Streptococcus species, and of the specimen source, 6 out of 9 were either a heart or prosthetic joint specimen. So again, this lines up well with our overall positivity rates, and it also matches what we already know from the literature as being high yield sources for testing by broad range. On the other side of the spectrum, there were far fewer specimens with high VIO scores, but of them, 7 out of 8 had positive broad range results. These identified predominantly Streptococci and Corynebacteria as the causative pathogens. And again, the predominant specimen type is from heart specimens. This system overall confirms that there is a correlation between the presence of inflammation and organism present in a sample and the broad range results. But to determine if any one of these variables is more predictive than the other, we used a Fisher's exact test and found that specimens with visualized organisms, both on pathology and gram stain, demonstrated a significant likelihood of broad range positivity. So for samples with organisms reported on pathology, the broad range results are 5 times more likely to be positive. And for organisms reported on gram stain, the odds are 80 times greater that the broad range result will be positive. So it makes sense that seeing organisms in the specimen is a good sign for being able to detect a pathogen, even using molecular methods. I'll also point out here that at HUP, all but 3 of these samples were sent on frozen tissue specimens. So the high positivity rate makes a lot of sense in that context, given that the same sample that was gram stained was also sent for broad range testing. So I've walked us through the bioscoring system, but I want to recap and put it all together in the context of stewardship decisions. In our analysis, there were 59 samples, the majority of the 86 included in the study, that had a bioscore of 0 or 1. Of these, 12 were positive and 47 were negative. Of the 12 positives, only 9 were considered pathogenic, meaning that a quarter of the total positives in this category were considered to be insignificant. And just for even broader context, there were only 4 samples in the whole study that were considered clinically insignificant, so 3 of them fell into this category. Of the 47 specimens with negative broad range results, over 80% of them were still considered to be an infectious process. And when we look at the practical implications of these results, mainly in how they change therapy, we can see that only a very small percentage of these negative broad range results change management. And that de-escalation really only happened in a very small subset of cases where they were confident in non-infectious etiologies. In the sample group with a high bioscore, there are far fewer samples, but the interpretation was more straightforward. All 7 positives were considered pathogenic, and the 1 negative result was still considered infectious, likely because of the high levels of inflammation and the organism seen in the specimen itself. And for these specimens with a high bioscore, most of the results did not prompt a change in management, but we think this is likely because they already had an organism reported either on gram stain or pathology. So the final identification was instead helpful to confirm the appropriate treatment plan, but they had already been narrowed. So I want to share a little bit about how this study has informed our stewardship conversations, especially with samples with a low bioscore or that are potentially have lower, we'll say lower yield samples. So what we now highlight in conversations is that when you send low expectation samples, you can generally expect them to be negative. So less than 15% of our low bioscore samples detected the causative pathogen. And furthermore, when they're negative, most teams aren't comfortable using this as a test of rule out to de-escalate or stop antibiotics. Of our negative results, less than 20% of them affected or de-escalated or stopped therapy. So when we think about the similar molecular assays that have a low positivity rate but might be more expensive, there are several tests that are pretty widely used within Clin Micro. For example, meningitis encephalitis syndromic panels are used primarily, despite the fact that they have an overall low positivity rate, they're used because they lead to de-escalation when they're negative. So this prompts the question, in the case of this test, we want to ask, if it is negative, will it lead to de-escalation? And if not, is it possible that there's less utility in sending these low expectation samples? So overall, to conclude this section of our analysis, we anticipate higher positivity rates in heart, CNS, and prosthetic joint specimens. In samples with a low bioscore, with this analysis, we can confirm a low likelihood of broad range PCR positivity. So we would caution against the routine sending of specimens in this category, with the exception, I will say, of high-yield specimens, such as prosthetic joints, CSF, and heart valve. We can also add from this analysis that negative results in this category appear unlikely to alter patient management. In contrast, specimens with a high VIO score indicate an overall high likelihood of positive broad-range results, which are unlikely to alter management, but can be helpful to confirm the suspected pathogen. Ultimately, a stewardship program can focus on some of these features to increase appropriate ordering of the test, and it also gives a benchmark to set expectations during discussions with the clinical team based on both the source and the specimen itself. And really what I think is most helpful about this system is that it takes a very open-ended test and it provides some structure to stewardship based on features that are readily accessible even without a multidisciplinary stewardship team. So I want to briefly discuss the limitations of the study. The first is that it is a single center study with a limited sample size. So this means we're, of course, biased based on the culture and training of the providers who are ordering and interpreting the test, as well as laboratory leadership and their criteria for approval of sending the test. Another feature that's worth mentioning, it is difficult to objectively evaluate the negative predictive value of this test in the absence of a gold standard. So the samples that are sent for molecular sequencing were sent because the cultures were negative. So we're reliant on clinical adjudication to determine that whether, despite negative cultures and molecular testing, if this process is still considered infectious. Lastly, and most importantly, this is a retrospective review, so it comes with inherent biases. HUP already has a stewardship program based on published literature as well as anecdotal experience. And so in some ways, it is a cyclical process as clinical experience is published, and then the studies, those studies that are published determine clinical practice. And it can become difficult to determine if we're missing key indications or if they're just low volume and being filtered out by our stewardship process. I will say that this cycle is in contrast to the use of this test in pediatrics, where the concern is less that of bias from retrospective reviews, but rather just a lack of published data. So to tie this back to the use of this data at CHOP, when we pivoted to applying some of these concepts, we encountered a few unique considerations. The first is just general challenges with pediatric diagnostic stewardship, which can be complicated by nonspecific disease presentation in kids, as well as a low risk tolerance for missing something and significant fear factor associated with uncertainty. Lastly, and most importantly, there aren't the data to support or advise for or against the use of this test for certain indications in a pediatric population. CHOP also has recently initiated a diagnostic stewardship committee. So in that process, we've experienced some of the challenges of enacting a new laboratory stewardship process, which involves many stakeholder conversations, as well as a very collaborative approach to stewarding something like this, which is a send-out test. It's not performed in a particular lab specifically, and so stewardship of that test becomes a little bit more challenging. But from this study, what I think we can make some broad conclusions about the possible benefit of stewardship. So in looking back through the CHOP data set, we found higher reported rates of polymicrobial contamination in specimens that were sent for broad range. So this could certainly be helped by discussion of the appropriate specimen sent from a laboratory medicine perspective. We also found that there was proportionally a much higher rate of failure to acknowledge positive results. So this could be due to a lot of things, but potentially due to pediatric patients moving more fluidly between healthcare systems. Ultimately, though, without a stewardship process in place, there's no way for the lab to either evaluate the specimen being sent or follow up on test results. And this, I think, is especially important for such a flexible and powerful test when you're really sending diverse specimen types for testing. So how does broad-range PCR fit in as a tool in the arsenal to diagnose infectious diseases? As we reviewed, there are several indications that clearly benefit from the additional information that this test can contribute. In adults, endocarditis, meningitis, encephalitis, and joint infections are certainly benefit from this additional information, as well as potentially others undefined, especially in pediatrics. Not only that, but there are studies that are less concerned with this idea of syndromic testing that have shown a generally high concordance of 16S compared to routine bacterial cultures. And these suggest that this could play a broader role in the lab in the future. But I would argue, based on our findings, that an approval process would be beneficial to guide the utilization of this test, both for specimen selection to minimize contamination, as well as tracking of results for a send-out test with a long turnaround time. And then for these rare clinical scenarios where you're sending atypical specimens, something like the VIO scoring system can help to add structure to which specimens are expected to be high yield. Lastly, I'll wrap up with the work that is still to be done on this project. These results have and will continue to guide our conversations with ordering teams about thoughtful utilization. This has also contributed to evaluation of our test stewardship process, both at HUP and certainly conversations at CHOP. More broadly, to better understand test utilization, multi-center studies could be helpful to compile data from smaller sample sizes like what I described today to identify specimen types with the highest clinical yields. And this is especially true in pediatrics. But ultimately, the best and certainly the most ambitious way to do this analysis would be to set up randomized clinical trials to evaluate patient outcomes using different diagnostic workflows. So this is extremely challenging for many reasons, due to low numbers of patients who could be enrolled who meet criteria, as well as expense and laboratory effort. But this is certainly a goal to aspire to as we work to understand the diagnostic tools available to us, especially in the era of rapidly expanding molecular diagnostics. So with that, I just want to briefly thank Dr. Laurel Glazer and Dr. Kyle Rodino for their support in this project, as well as Dr. Rebecca Harris and Dr. KP Smith at CHOP for their input as well. And thank you for your attention.
Rebecca, thanks so much. That was really a fantastic talk. I can say that you reviewing and putting like numbers to the data that we have has been really helpful. I feel like a lot of us who try to make these decisions about the utility of the test have gone with our experience and feeling, but it's nice to see that there's what we thought to be true as far as success is probably actually true based on what we see with gram stain and pathology. There are a couple questions in the chat. Jason and I are going to run this together, so maybe I'll read the first one. He can do the next one. We'll see what else pops in. I have a couple questions too. The first one I see is from Dieter, and he asked, for broad-range PCR, how frequently do you receive back a result that has like a new 16S sequence obtained, and how are they interpreted for the clinician? Sort of new bug, or could it be sequencing error? How are you attaching some clinical validity to the result?
That's a great question. So because we have this test under active stewardship, I will say that any identification that it falls outside kind of our typical realm would get discussed with the team directly. But in our review of this data, we didn't have any results that fell kind of into this bucket of something that we would second guess the identification.
All right, I have another question. This is from Irv in the chat, and I think you've addressed this, but maybe you could expand on it a little bit. So he says, how did the positive broad-range PCR results correlate with conventional culture results?
Yeah, so generally we didn't have very many samples falling in this category because we were waiting to see if cultures were negative prior to sending out the specimens. But for those specimens where you had, you sent for broad range and then the culture grew something, we found 100% concordance. So I think there were only 3 specimens that fell in that category, but they were concordant between culture and broad range.
For the ones, Rebecca, that had positive gram stains, did the broad range result at least correlate with what you were seeing on that gram stain?
It did. So in all cases, when we had a positive result from sequencing, it matched the gram stain.
I have another question for you. Great talk, Rebecca. So, you know, you spent some time talking about VIO scores, and from my calculation, it looks like, you know, 15% of the samples with low VIO scores, you know, yielded some positive result. Where do you set a cutoff that where something is valuable in terms of yield? And that's always a discussion when you talk, you know, there's a difference between no yield and some yield, particularly in difficult to diagnose cases. And so, you know, is it unreasonable to say, well, look, there's a, you know, 10 or 15% chance that, you know, these low VIO scores are going to yield something. Is there a way to put some kind of economic value to this whole model? You didn't really discuss the economics in terms of the total cost, the cost per positive. Does it avoid other downstream costs, even though it might be low yield? Could you address some of those issues?
Yeah, it's a great point. And actually, even the case study that I opened with, the case of the Cardiobacteria hominis, that fell into the VIO score. It fell into the category of a VIO score of 1. So if we were going purely based on the numbers, no, that specimen wouldn't have been sent. But I think adding on the caveat of, we know that heart valves are generally high yield sources. So that would be one that we would consider sending despite potentially the numbers not looking great, as well as, you know, CSF or joint infections, certainly. So I would add that kind of caveat on almost all of those positives in that low VIO score fell into one of those high yield categories. So we can kind of recover some of that in that category. In terms of the economics, I didn't go into that with this analysis, but that would be, I agree, a really interesting addition to the study.
Thanks.
And there's another comment here from Vincent with a question. So he says, thanks for a very interesting talk. And the question is, while it's very informative to ID the bugs based on 16S, obviously, due to the genetic diversity and difference in expression, how can these results, or are they used to inform antibiotic resistance, sensitivity, toxin production, lots of other players involved?
Certainly. I will say that this was something that I went back and looked at to see if there was any question about, because of course with molecular testing, you don't have susceptibility results. And in the cases where we did see a de-escalation in antibiotics, it was universal, all except for one case, were willing to de-escalate based on the identification alone. There was one case where ID was hesitant based on the lack of susceptibility data, but for the most part, it seems like the identification for these cases was enough information to help inform the change in treatment.
One more question in the chat from Hamid. He asks, what's the cutoff for differentiating something that's a commensal or could be commensal, like staph epi, is the cause of infection, or it's a product of contamination that's noticed in the sequencing?
It's a great question. This is not a quantitative assay, so we don't have a cutoff per se. For the purposes of this study, it was based on the clinical team's interpretation of the results and whether or not they felt it to be a true pathogen versus a contaminant. But this is a conversation that we have frequently, right? We have it with any testing modality where there's some chance for contamination, the discussion of whether or not it is truly a pathogen or coincidental.
Rebecca, I'll ask you a question, kind of builds off of what you mentioned with Irv's question, that a lot of these where we let the cultures go, then you make a decision about broad range after the fact. How challenging is that to operationalize, where you are essentially trying to do testing on a sample that you already did a bunch of work up on and you weren't quite sure you wanted to do this test to begin with?
It's definitely a challenge. It depends. Certainly, it's going to depend on the specimen itself. So something like a heart valve, where you have very little material to work with in the first place. I think as we formalize some of these recommendations, you can have kind of upfront setting aside of specimen in the event of molecular testing down the road, especially if you know that there has been prior antibiotic treatment. I think that's something that ID should be aware of and should be asking for, as they're the primary users of this test, at least at our institution. But in terms of the kind of practical downstream effects, I think it has to be the potential for molecular testing has to be in the mind of people before the specimen goes through its entire workup, or else you won't have any unprocessed specimen left to send for molecular testing. So that's again where having the test under stewardship can flag it from the lab side of things, and we can reach out and have that conversation.
Great. One more follow-up from Dieter. If I understand correctly, you get the 16S RNA result, you look at the databases and identify the bug.
Yes, to clarify, so because this is a send-out test, all of the bioinformatic matching of the sequence to a database is done by the reference lab. And so the report to us is either a single organism, no DNA detected, or of course, if it's a polymicrobial result, then you'll get a list of organisms. But we are not doing the bioinformatic analysis on our end to match the sequence data to the.
So that's why I'm a little curious, because all your results are based on the quality of your data banks. And as a veterinarian and interested in zoonosis, your data banks might actually be very poor. To think about the possibility of all these bugs, which might cause problems in immunocompromised people or people with pets, I don't know, who actually might absolutely not be discovered and might be in your negative results because you don't see the 16S RNA and you don't even try to look at the possibility of a bug in which is not in the data bank, or something new, correct?
It is certainly a possibility. We are limited by not doing the test. We are limited by the information that the reference lab provides to us. And of course, if you're doing something like next-gen sequencing, there is, of course, a depth to which you're able to kind of mine that data, or even, like, as you mentioned, the quality of the database or the breadth of the database to which you're comparing to, that you could potentially be missing newer, not uploaded identifications. So that is an inherent limitation of using our reference lab for this assay.
So for a clinician, it remains always possible. Any negative result doesn't mean too much.
So just a comment about that, Dieter, because it's a good question. So the labs that we use, the reference labs, are CLIA certified laboratories. They're CLIA licensed laboratories. And then they may have other certifications like CAP, licensure on top of that. And for them to provide this test, they have to have, very clear validation studies for them to be offering that. So I don't think it's random in terms of how they choose, their organism ID. They have to have criteria for doing that. And I suppose you could probably request, what databases do they use? Probably not easy to get their validation data, but there is, behind the scenes validation of their process. Now, I mean, the microlab at HUP, does their own sequence analysis for organism ID. And I mean, you might want to comment about that, Rebecca, in terms of just doing our own sequence identifications and how that's done, and are there criteria that you use for internal identifications?
Yes. So what Irv is talking to is kind of a different application. Instead of direct from specimens at HUP, we will, for isolates that are not identifying using by MALDI or biochemicals, we will perform this assay of PCR of the 16S gene and send that out for sequencing ourselves, get the raw sequencing data back, and then do our own bioinformatic analysis where we are looking at quality metrics. It's a much simpler process than what is necessary direct from specimen, and it doesn't fall under the same kind of regulatory requirements that the full-on validation that would be performed by a reference lab. But that would be kind of an alternative application of how to use the technology.
Peter, I'll just comment with you that having trained at Mayo Clinic where the test is actually done, I've only seen once where we got a sequence result that was like low confidence and confusing. And the way that they're really approached is like, it becomes a lab director to lab director conversation of, there's bacterial sequence here. The database that we're using is giving this result that is sort of low confidence or low quality. We can use essentially like broader databases, like you can end up blasting this, where there's the risk of what's in there is not accurate or correct from a clinical standpoint of what we would report. But then you go and dig into the literature and start looking at the references, sorting out how well do you believe the sequence of what's there. And it becomes really like a conversation. As Irv's mentioning, that you can only validate so many organisms and so many sequences, and the clinical test has to be rolled out without seeing everything under the sun. But you sort of take a very measured approach, I'd say, gaining lots of experience with your test and deciding, is this a sequence that is of the quality in which I would report, and how would I report it if you haven't seen it before? All right, we're past the top of the hour. Lots of great questions. And Rebecca, again, fantastic presentation. Thank you so much for joining our group. Vincent, anything to add before we adjourn?
Nope, I don't think so. Thank you very much. And thank you for all of you attending.
Thanks.